Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with David Jones of Infineon. We're going to take a look today at what's going on with sensor fusion. David, we've seen a lot about sensor fusion in the automotive space. Where is that today, and why is that so important?
The automotive industry is going to fully autonomous driving, at different levels of autonomous driving. And part of the sensing for the vehicle is the inputs coming from various sensors. And sensor fusion is very well known in that space. You've got things like camera data, you've got radar, you've got ultrasonic, you've got time of flight. They're all doing different things, and they're all sensing the environment round about the vehicle. The vehicle needs that data. It needs that information to process the algorithms for fully autonomous driving.
Is it starting to move into other markets now? I mean, you think about automotive, most of that was done for economic reasons, right?
Yeah, we've seen a big push into the consumer space. So whereas in the automotive space, typically as a supplier of sensor technologies, we would provide the sensors to the automotive industry, and then they would put the smarts around that. Either the automotive manufacturers themselves would develop all of the algorithms and the technologies required for autonomous driving, or they'd work with technology companies or acquire technology companies to bring that in-house. And those techniques are owned by those specific users. Clearly, that's a different model to addressing this in other marketplaces. And what we're seeing now is a move towards, we call it sensorization, now in the consumer space. And the same concepts of sensor fusion, which is one sensor can do a job, but two sensors or three sensors can do that job much more efficiently. We're seeing that now being deployed into consumer applications. And the big issue there is not capabilities to do that, but similar to automotive, where all the processing is done in the vehicle itself in real time, that requirement is also required in the consumer space. Although these can be connected devices connected to the cloud, because of delays, because of the amount of data produced by sensors, there's a requirement to really manage those sensors in the edge device itself. One of the fastest markets we see sensor fusion being deployed is in the smart home IoT market, where there's a lot of smart devices now being developed, but they're very prone to giving a lot of errors, either false positives or false negatives, say, for example, an alarm system. And by using or deploying sensor fusion at the edge, we can get around a lot of the issues that consumers are currently seeing within those devices.
So let's dig into this.
Sure.
David, what are we looking at here?
This is what we've been working on, which is if we're going to interact in the consumer space with machines, we really need to look at mimicking how we as human beings interact with one another and mimic those sensors. And so our sensor technology has been developed to really mimic how humans interface with people. So we talk about things like hearing. So smart hearing, smart ears is obviously microphones. And in the microphone space, we develop very high sensitive microphone devices. When we look at sight, we have two technologies that we think are very applicable to interacting with machines. And this is a radar technology and 3D time of flight. So unlike cameras, which is also a way to interact with devices, this is really focusing on the 3D aspects. As we see objects, we see them in 3D, and similarly to sense those objects, we deploy these technologies. Pressure, that's really touch. And then we have environmental sensing, which is smell. And so we have sensor technologies essentially mimicking the human senses. Other than taste, I don't really know how taste comes into interacting with a machine, but these are the sensor portfolios we put together. And then by merging these in a sensor fusion architecture, we can basically have a very intuitive way of interacting with machines.
And as you put these things together, you can do more than you could with individual sensors too, right? So they can all work together as we're going to put this in the perspective of, okay, for example, if you have glass breaking, you can put a pressure sensor on there, you can have the audio, and you can combine those to say, okay, this is actually happening. It's not just some glass that's broken in the background.
Correct. And that's a very good example, because the sensor technologies that are out there to detect, say, for example, a glass break sensor it relies totally on that audio sound. I would say it's a very non-intrusive device, which looks at roughly sounds that sound like glass. And the problem with that is that because audio is such a difficult technology to process, there's a lot of sounds which sound very similar to glass break. The result of that is that those devices, they end up sending a lot of false positives or false negatives to the user. So if that's a connected device, for example, within the home, you'll get an indication on his smartphone that, hey, someone's breaking into your house. And it may be something like somebody's rattling some cutlery in a drawer, and that sounds very similar to the sound of glass break. And we want to avoid that. So by adding a pressure sensor to that, we can actually combine the two. So we have the audio and we have the pressure event. Because what happens when you break glass is it physically bends. And our sensors are so sensitive that they can detect that pressure event within the home. So the combination of both of those ensures that you have a very high reliable alarm system by applying sensor fusion technology to that.
So where else are you seeing this being used?
Yeah, so we see applications in the home for air quality, HVAC systems, for example. We see areas of smart appliances, lighting, entrance devices, and panels and control systems within security environments, thermostats, for example. All of those devices require some interaction with human beings, and a lot of those interactions today are not necessarily intuitive, or the interactions are not very reliable. If you take, for example, a PIR sensor today, there's a lot of things that can trigger a PIR sensor without even the presence of somebody being there.
One of the problems that you deal with as you start getting multiple sensors and trying to get some intelligent results out of fusing this together is that you have to partition the data properly, and you also have to prioritize what's important to you. How do you go about doing that? So take it, for example, the glass break sensor. How would you know what's the most important data there?
Yes, good question, actually. We actually, on the glass break sensor, we actually built a complete end-to-end solution. So what was important for us was we had to gather initially the data for glass break. Now, what we wanted to do specifically when we looked at a glass break sensor within the home is we wanted to go into a home and physically smash the glass that was in that environment. So rooms are different from, setting up a panel in an office and smashing it, for example. We went into houses. Fortunately, we were in a position where we found some houses that were due for demolition, and we could go into those houses and then smash the windows. And literally, we looked at, the different size of the pane of the window, the size of the window, whether it was single pane, dual pane, what was in the room, whether the room was empty, furniture, those types of disturbers. And then we smashed glass. We smashed about 3,000 events with different devices, with hammers, with sledgehammers, with crowbars, to get the data we needed to develop an algorithm. And that algorithm became our sound algorithm. At the same time, we could also measure those pressure events. And with that data, we could then develop the sensor fusion architecture to do that. Now, the original development was done on a Raspberry Pi. So a lot of performance in the device. It's a quad core running at a few gigahertz. The challenge was really getting that data, doing that analytics, and then applying that into an edge-based device. For many of these sensors, a customer's not going to pay the cost of a large system-on-chip device. These sell as DIY kits, for example, that hook up to a hub. We had to basically get to a point where we compressed all of that data and that algorithm down into an embedded MCU application. And we deployed an embedded MCU based on a Cortex M4 device, for example, which is commonly used in a lot of these devices, and then compressed the algorithm without losing accuracy to develop the overall solution.
How much processing is done at the sensor level versus in a system that the data is being sent to?
Pretty much most of it. The way we're architecting this and the way a lot of these devices work is the information that goes to the cloud is really the result. The last thing you want to do is you want to look at all of the sensors and just send complete raw data from the sensors to the cloud. It's a lot of data to process. B, there's inherent latency in doing that. And by the time the alarm system detects an event, the burglar could have come in and out and stolen something within the home. And there's no point in even detecting that alarm by the time it gets to the user. So literally everything has to be processed in the edge.
Can you put AI machine learning into the edge device here with the all the sensors and say, okay, we understand what this is now, we can actually get more granular with it?
Yes, and what's happening, the way the industry is moving is these embedded cores are available today, and you can either do an MCU base, you can do a DSP, and what's also interesting now is that these AI learning, these machine learning neural networks essentially that process these algorithms can now be squeezed into microcontroller designs.
In the past, we used to think about, oh, we're going to run gigabytes of data here and we're going to need massive processors. Reality is on the inference side, you can really boil that down to much smaller amounts of data, right?
That's correct. And some of the sensor technologies we use are not necessarily as sophisticated as a full RGB camera where you want to collect full 4K resolution. With time of flight, for example, you can get very good identification for much less data processing with those particular sensors. Yeah, the challenge really is today, where we are today, what we can do today will determine the number of sensors that you can add in a sensor fusion design. But if you look at what's happening in terms of the processing capabilities going into the edge, if you extrapolate that 2 to 3 years, you can see that there's more and more sensors that can be fused together to provide those results. On the flip side of that, the more sensors you add, the more cost you add to the system as well. So unlike automotive in the consumer space, there's a trade-off. 1 sensor is good, 2 sensors is better, 3 sensor may get you the best results. So for example, if you added radar to this to detect also the presence of a person, but is the end customer going to pay for that additional cost?
So how do you see this playing out in other markets? What's a real world example for this?
Yeah, so another real world example would be a smart speaker. So today we interact via voice commands. Hey Alexa, hey Google, those types of commands. But what if that speaker was more intuitive? So for example, a number of people within a room, can the device detect, how many people are there and make the interaction between those people more intuitive? Are the people approved to be there? There might be that smart speaker could also be used for security reasons. Are the people supposed to be there? Who's in the room? So we can use our time of flight technology to basically look at faces and compare them to registered faces of users that are using the system. And that can detect who's actually there. So you can customize the smart speaker interaction with that person. That person may be more interested in music than talking or getting information. Another person, like a child, could be more interested in some educational features. So it customizes the response to the particular user. Where is the person located in the room? Because a lot of stuff that you can do beamforming with the microphones to point exactly to the user. So you have a better interaction with less errors when you're speaking to the device. And is this natural human sound? In other words, is the speaker being triggered on a TV or a radio event? Or is this like natural sound? We can process the sound in the device to determine that that's actually a human speaking. That's not something coming from television, for example.
So what you're doing is you're able to take sensing and put it into context of what's happening around it, right? Much higher resolution of basically whatever you're trying to do.
Correct. Yeah. So if how can I help you in this case? And if I take that one step further, we can point this down to a specific sensor. So if you want to anticipate what we want, you can do that with a radar device. So radar, if you think about it, is like your eyes and then the microphone. So we're trying to anticipate what you're looking for, understand who we are. So time of flight can give a 3D image on who that person is, and then you can redirect the specific interaction that you want with the smart speaker or the smart speaker device, how that person normally uses the data provided by the smart speaker, or the body language detection. When we interact, you would think that voice was the big device that we interact with, but a lot of it is body language. Our motions, how we interact with our hands, etc., is a big part of how you interact, making that less intuitive. And we can do that with the time of flight, for example, and also radar technology. So those things going into body language detection. to make the interaction more intuitive.
When an engineering team builds a system and they're trying to incorporate this technology, what sort of problems do they run into in terms of storage, power, noise, other things?
And that's changing on a day-to-day basis. So the sensor technologies are being miniaturized. So for example, our pressure sensors, microphones, they're all MEMS-based technologies. That technology is shrinking down very rapidly. Radar used to be a big device with massive antennas detection. Now that's going on to tiny slivers of silicon where we've embedded the antenna design into the package itself. And similar to sensor technologies, the sensors themselves are getting smaller and smaller. So now we're moving away from complete sensor systems, big devices, and literally shrinking this down into semiconductor devices that can be placed on a printed circuit board. The second innovation that we're seeing is the edge-based AI technologies and really pushing machine learning to the edge with smaller, still intelligent networks that we can implement directly on silicon. So the silicon size is shrinking down quite dramatically to provide a cost component that makes it more cost effective to implement these in consumer devices today.
As you start adding more sensors, though, they don't necessarily age at the same rate, right? So how do you account for that? How do you calibrate these to make sure that everything's still working in sync 5 years down the road, 10 years down the road?
A lot of devices today are connected. So either the device connects directly with Wi-Fi to a hub, the hub sends, or the gateway sends information to the cloud. A lot of these devices are managed in the cloud. So what that means is that you can continually calibrate the device, you can update the device, you can securely download new firmware, you can upgrade the device. So from an engineering perspective, you can build a product today knowing that in 3 to 4 years that the technology is going to advance, there's going to be new algorithms that you can do more and more stuff with the sensors and push that to the edge.
So where else are you seeing this getting used?
In the time of flight, we see areas of facial recognition. We see AR and VR applications, so really driving those smart glasses, goggles for gaming applications, those types of areas where we're seeing this being pushed. If you look at cell phones, for example, they use either radar technologies or deploying time-of-flight technologies in the sensors themselves. So you can do things with the phone. You can recognize the person. You can switch on the mobile device based on someone's image, or in some cases, customer that we worked with, you can actually put a hand up to the camera and you can detect the vein patterns within a hand or a thumb or a finger. So just by going close to the device, it switches on, it recognizes the vein pattern within the user. On the radar side, this offers many, many opportunities. We're pushing both 24 gigahertz and 60 gigahertz. 24 gigahertz is a good technology for outside and long distance. 60 gigahertz has much greater resolution. What we mean by that is millimeter resolution. So we can actually move to very small gestures. The movement of fingers can be detected. You can use your hand to replicate a dial being moved. So you don't need to touch a device. You can actually interact with the device without touching it. Again, more intuitively. Ultrasonic, we have microphones that run in the ultrasonic band. So rather than just hearing events, which is what they do naturally with in situ, they're also running up to 40 kilohertz or higher, which you can't hear with the human ear. But those sound waves can be used to bounce off and detect objects. So you get very fine resolution by leveraging that microphone.
So given all of this, are you starting to see much more interest in putting these sensors together? I mean, in the past, people bought sensors and they were being used sort of independently, but putting them together in a module is a much tougher job. Are you starting to see this roll out on a pretty regular basis?
Yes, we are. Yes, we are. The market knows that sensor fusion is the right way to go. That, yeah, you can get a lot of data from one sensor, 2 sensors is better, 3 is even better, maybe even 4 in a system. What's happening now is that because of the cost points coming down, because of what the semiconductor industry is doing in terms of driving the devices to be physically smaller, is that there's more and more interest. The biggest place that we're seeing this is now in security is a good example. Security systems within the home. Those fundamentally are very unreliable today. systems. So by adding sensor fusion, you can make them much more reliable. And what's often the case is when we get into those discussions on quality and reliability, it's less about the cost of adding this. It's more about the user experience and what sort of experience they're having with the products. And so what we're seeing is this huge drive to get better and better quality products out there.
David Jones, thanks for a great explanation.
You're welcome. Thank you very much.